Hi guys, so today we're going to do something a little different. This is the Leetcode Biweekly contest 53. So that's what we're going to do today. And I'm not going to solve the contest because like only 15 minutes are left. I don't think I can do all these problems in 15 minutes. And like I was a little busy while this contest started, so I wasn't able to attempt. But I read the problems on my phone, so I think I can do these. But yeah, so anyway, first of all, I am not a regular lead coder. Like, I don't know what the word is, but yeah, I don't regularly do these things on lead code. So I'm actually a competitive programmer. I think top 15 or 20 in India, or top 10 maybe. So yeah, so this is actually pretty easy for me. All right, so what I will be doing right now is I'll just be giving some ideas for how to solve these problems. Right, so we have these four problems. Let's start from the easiest one first. Okay, so this first problem is actually, I think, pretty easy. Uh, it's actually too easy. What we have to do is we are given some string like this A, B, C, B, C, something like this. And what we have to do is we have to check all strings of length 3, all strings of length 3. And in all of those, what we want to do is we want to see how many of these have all characters different. For example, this one does not have all characters different, A and A are matching, but in the other strings, all characters are different. So we want to print the number of strings that have all characters different. So what we can actually do is I'll just write some code on my editor so you can try to understand what this is. Yeah, so it will be something like, yeah, yeah. So we will have something like this. Okay, let me write it here only. And we zoom it. Okay. Yeah. So what we will do is we will iterate on the string. So let's say int n equals s dot size, and then let's iterate on the string. For int I equals, let's start from I equals 2 because we want strings of length 3, right? So the first string will be of 2, 3. Yeah. So I'm starting from the index 2 because, for example, I'm iterating on this character, right? So if I start from here, I won't have any string. So I want the string that is formed using uh, I minus 2, I minus 1, and I. So I want to check if these three are different, and then I will add 1 to my answer. Let's say int answer equals 0. Then answer, I have to return the answer. So return the answer. And yeah, so if these three are different, then we have to increase the answer by 1. Something like if si not equal to si minus 1 and si not equal to si minus 2 and si minus 1 not equal to si minus 2. And that means pairwise all three of them are different to each other. So if this happens, then we can just increase the answer by 1. And yeah, so this will work. I don't want to submit it because I won't be able to do all the problems in 15 minutes. But yeah, something like this. So that's what we can do. In this one, what we have to do is we have to pair, we have an array of n numbers, and we want to make n by 2 pairs such that each element is exactly in one pair, and the minimum uh, like the maximum sum pair is minimized. So what is the maximum pair sum? Maximum pair sum is the take all the pairs, take this sum, and take the maximum value from that. So obviously it makes sense to like first of all let's sort the elements. So whatever the elements we have, let's just sort them. So then we will have the elements in ascending order like this. Let's say 1, 2, 5, 7, 9, 12, something like this. Right. So we will have an ascending order. So if we take the first element, since we want to maximize the minimum pair sum, what we will do is we will pair this with the smallest element that is there, right? So the biggest goes with the smallest, the second biggest goes with the second smallest, and third biggest goes with the third smallest. So what we have to do here is something like, first of all, we need to sort them. Sort nums dot begin, nums dot end. I hope this works here, right? After we do this, what we will do is we will take some variable answer, okay, and we want the maximum, right? Like we want the minimum of the maximum, so we will store just the minimum, and we are greedily assigning them each other. So something like, we also need n equals everything is positive, right? Yeah. So n equals the nums dot size, and then what we can do is we can just run a loop for int I equals 0, I is smaller than n by 2, because we only have to make n by 2 pairs, I plus plus. And here what we will do is we will pair I with n minus 1 minus I. So I comma n minus 1 minus I. That is first element from the beginning and first element from the last, second element from the beginning, second from the last, and so on. So something like this we have to do. And yeah, so then it being right. So just take the sum, and we want the maximum. So answer equals maximum of answer comma uh, nums I plus nums n minus I minus 1. So once we have done this, we just have to return the answer. And yeah, this should work. Let's see the third one. I am definitely not going to write the code for this one. It's a little implementation heavy, I would say. But I'll tell the idea. So in this, what we have to do is we have to take the rhombuses like this, like how they have explained. These are actually like 40 squares that are rotated by 45 degree. Yeah, square rotated 45 degrees. And then we want to take 3 distinct rhombuses and their sum, the rhombus sum, something like, let's say if you have these elements like this. So sum of these elements is like a rhombus sum, and we want the maximum 3 distinct rhombus sums. So if there are less than 3 distinct, we will just return one of them or whatever. Right. So what we can do here is we can just find all the rhombus sums, then sort it, and then unique it and take the biggest 3 values. Or if there are less than 3 values, just how many are there. Just take all of them. Yeah. Anyway, so first of all, this is helpful that the grid length is smaller or equal to 100. So yeah, so that is really helpful, that grid length is smaller or equal to 100. And why is that helpful? So that's helpful because if you take 100 multiplied by 100 multiplied by 100, this is not a lot, this is just 10 to the power 6. And why am I doing this thing? So if you look at a grid like this, something like this, what's actually happening is any rhombus can be defined by just 3 parameters. Okay, let's take this rhombus. Yeah, so it can be defined using just 3 parameters. And the parameters are, first of all, you have the height, right? Because the height and width are the same. So just the height, or maybe this length can be a parameter. So any length or some height or something can be your one parameter. The other parameter can be the x coordinate of one of the points and also the y coordinate. So you only have 3 parameters, x, y, and h. If you choose 3 parameters, the x coordinate of a point, the y coordinate of a point, and then make a rhombus by taking that height. So from anywhere I can start. Let's say I start from here. If I take the height equal to 3, then if I start from here, obviously I can make a rhombus, right? So how many possible values can they take? So x can take up to 100 possible values. This can also take 100 possible values, and this I think can only take 50 possible values, but still that is less than 100. So yeah, this thing is not very big. So what you can do is you can actually find all the rhombus sums, put them in a vector or something, sort everything. In fact, you can put all the rhombus sums in a set, and from that set you can take the biggest 3 values and just return that vector. So yeah, so that you can do. But one question that remains is that, let's say if we have chosen the x, y, and h, let's say we have chosen the x, y, and h. How do we find the sum of this rhombus in constant time? So the any rhombus can be broken into four parts: this line, this line, this line, and this line. So let's name these lines A, B, C, D. Right. So the total sum of the rhombus is like A plus B plus C plus D minus this point, minus this point, minus this point, minus this. Why am I subtracting these points? Because these points are actually covered twice in all of them, right? Although maybe we can make sure that we consider these lines leaving these points in one of them. Maybe we can work that out or something like that. So maybe we can make the lines like this. Something like, let's say this is one line, then this is one line, this is one line, something like this. Maybe we can do. But yeah, so the obviously it is not difficult to eliminate the single points in constant time. What is actually difficult here is to actually get the diagonal sum. So we want to get diagonal sums of various diagonals. Let's say in some case we want the sum of this diagonal or this diagonal or any diagonal. So we want the sum of any diagonal in constant time. How do we get the sum of a diagonal in constant time? So for that, what we will do is we will do we will do two things like this, because there are two types of diagonals: the leading diagonals and the non-leading diagonals. Like the ones that are pointing in that direction versus the ones that are pointing in that direction. So yeah, so there are two types of diagonals, and for that, what you will do is you will do two times the diagonal prefix sum. So you will do something like diagonal prefix sum. So what is actually a diagonal prefix sum? It is something like, let's start from this point, and here we will store the sum of this element. Then at this point we will store the sum of these two elements. Then at this point we will store the sum of these these three elements, and here we will store the sum of these four elements. So how can this help us in getting any diagonal sum? So let's say, for example, if we want to get the diagonal sum for this, what we can do is we can take this diagonal sum, diagonal prefix sum, and let me actually take a different color and that it is really visible. So if you want this sum, what we will do is we will take this sum and subtract this sum from it. So what will happen is we will be left with this sum, and in that way we can get the sum of any diagonal. So we have to do a diagonal prefix sum twice. Why twice? One for the this type of diagonals and the other for the this type of diagonals. So only two types of diagonals are there. Just perform a diagonal prefix sum, and after that, by choosing the x, y, and h, we can get the sum of any rhombus, and then just put everything in a set, and then take the greatest three elements on the set, make a vector out of those. If there are less than three elements, however many elements are there, just make a vector out of those, and yes, that's it. So then return that vector. So I'm not going to write the code for this one because only 1 minute is left in it. So yeah. Lastly, we have this problem: minimum XOR sum of two arrays. So in this, first of all, it is important to see that the constant is actually very small. There are only n is only smaller or equal to 14. But I think we can solve this even for n is smaller or equal to 200 or something. So I'll be talking about how to do that, but it's unrelated. I don't think it falls in the Leetcode level. But if you're still interested, you can watch the later part of the video in which I will be talking about how to solve this same problem for n smaller or equal to 200. Maybe 200 or 500 or something. But yeah, anyway. So this one is minimum XOR sum of two arrays. So what is the XOR sum of two arrays? So it is something like you have two arrays, one array like this and the second array like this. So what we will do is we will leave the first array as it is, but we can rearrange the second array in whatever order we want. So it is something like we can pair these elements at any index that we want. We can pair them as we wish. And once we pair these elements like this, by rearranging the second array, once we pair them like this, what we will do is we will take the XOR of these two elements, then the XOR of these two elements, these two elements, these two elements, these two elements, and so on. After taking all those XORs, we will add everything. So add everything, and I think we want this value to be minimum. So yeah, so we want the XOR sum to be minimized. So how to do this? So n is actually very small here, so there's actually very simple solution here using bitmask dp. What we can do is we can use bitmask dp here, right? So how do we do it with bitmask dp? So the state will be kind of like dp of x comma mask. Okay, so what are x and mask? So you basically have two arrays. Let's say this array, that is the first array that you won't rearrange, and then this is your second array. Okay, so this is your second array. This one you can rearrange. So what we are storing in these DP states is the x and the mask. So what is the x? X is like a pointer in this. X is like a pointer which signifies at which element we are present right now. So we will process this in increasing order. So if we are at x, that means that we have processed all these elements in the array, in the first array. And what does this mask mean? So mask is like a bit mask of 14 elements. So what is the bit mask of 14 elements? It is like a number, a binary number of 14 digits. So something like this we have, right? So we will have 14 digits in total, 14 or n, whatever the n is, n digits in total in this mask. And what's happening here is wherever you have a 1, it means that this element you have already paired up with something. So for example, if we let's take an arbitrary state in the DP. So yeah, okay. So let's say we have already processed the first 3 elements and joined them like this. A second, like 336 with 6. Yeah. So let's say we had done something like this: join this one with this one with this one, and this one with this one. Okay. So what we know is we have moved till index 3 here, right? So index 3, so that becomes our x. That means x equals 3. And what happens with the mask? So let's put a 1 for any element that has already been paired and 0 for all the other elements, like this. So yes, so this becomes our mask. So this is our mask, and we can easily store this. So we can read it like a binary number. So what will this number represent? So this is like 1 plus 0 plus 0 plus 8 plus 0 plus 32, I think, right? Yeah. So this is 41. So this entire state can be represented by the number 41. All you have to do is take the binary representation of this, and based on that, you know wherever zeros are present, that element is not taken. So yes, so like this, you will do dp of x comma mask. And how do we actually do the transitions? So to do the transitions is actually pretty simple. What we will do is we will do dp x plus 1, some new mask. It will be like obviously you want the max. We want the minimum, right? Right. So it is the minimum of the like minimum of all the indices that are present. So minimum such that index I is 0 in bit mask, in mask, something like that. So like we want to iterate on all these indices where the mask has the bit 0. And what we will do is we will wait a second, we are assigning another bit, right? So yeah, so we can take something like in the new mask, wherever the bit is 1, we can try to turn it off and see which mask is the best. So I'll give you an example. Something like, let's say if you want the answer for this mask, how do you get the answer for this mask? This can come from only 3 different places. So one way of getting it is this, the other one is this, and the last one is this. Right, so only 3 of these are present. At max, how many can be there? At max, there can be only 14. So 14 at max can be the transitions. And yes, so if you try to do it, the total time complexity will be like O of n square into 2 to power n. Something like this will happen. So how did n square into 2 to power n come? Where did n square into 2 to power n come from? So this thing can have n different values. This thing can have 2 to power n different values. because you can see this is a bit mask of width n, and at each index you can have a 0 or 1. So you have two choices at each index, and there are n choices, so it becomes 2 to the power n. And yeah, so that's it. N into 2 to the power n states, and in each state you can have up to n different transitions. So it becomes O of n square into 2 to the power n in total, which will definitely work for n equals 14. I think it should also work for n equals 18 or 19 at least. At least maybe even n equals 20 it can work. But yeah, anyway. So yeah, so that was the solution for this problem. You can try it on your own. You can even try to write a recursive DP for this. That might be a little easier. With Bitmask is actually a little easier. But anyway, so and in fact you can make it a little faster. Instead of O of n square into 2 to the power n, you can make it O of n into 2 to the power n easily. So how to do this optimization? It's actually pretty simple. You don't have to store both x and mask. So the reason you don't have to store both x and mask is that um, in the mask, the number of set bits will be equal to x only. So like this information is kind of redundant. So you don't really need this. You can just ignore this, not memorize it, and your solution will still work. So in that way, you can easily bring it down to n into 2 to the power n. Then it will easily work for n smaller or equal to 20. But now let's do some bonus. Right. So this is not related to the contest. If you just wanted to watch the contest solution, then you can stop watching now. So you can stop watching. Otherwise, it might even confuse you a little. It can confuse you a lot. Like most probably, you don't even care about this. But anyway, so this is the way how to do this problem for n smaller or equal to 200, I guess. So this is actually a MCMF problem. So what is MCMF? MCMF is like min cost max flow. That is like a min cost max flow problem. And what we will do is we will take both of those arrays like this. Let's make a bipartite graph like this with both the arrays. And what we want to do is we want to make a certain matching in these. Right? So that's what we want to do. This is the first array, and for each element of the first array, we want to choose an element from the second array. What we can do is we can assign, we can actually make a graph like this. Then we can make a source and a sink like this. This becomes our source. This becomes our sink. And what we will do is we will like put water here, and we want the maximum water coming out from here. Maximum water that is coming out from here. But and these are like pipelines. So all of these pipelines have capacity 1. Capacity equals 1. And they also have some cost. So the cost of a pipeline will be the XOR of these two numbers. Okay. The cost equals the XOR of these two numbers. And then you can make all the n square edges like this. So in total you have n square edges and 2n vertices. And then I don't think it will work for n smaller or equal to 200. Maybe for n smaller or equal to 100 it might work. Because as far as I know, what is the time complexity of MCMF? I think it's n cube or something. Wait a second. Cohen's algorithm? No, we don't want Cohen's. We want the one that gives us weighted bipartite. Or we can see MCMF also. Min cost flow, I think. Yeah, like this. So what is the time complexity? Yeah, so I think it is n square into n cube into m. Okay, so this is I think n to power 5. Maybe it won't work for so it won't work for n smaller or equal to 100, I think, because n to power 5. But maybe for n smaller or equal to 50 or something, it can work. So yes, so this is like a polynomial time solution. So the biggest bonus is what I called it like a bonus is that we have a polynomial solution for this problem. Polynomial solution. So a lot of times a polynomial solution itself is a very big thing, because if you look at the bitmask DP solution, even though it's simple, it is actually exponential. So it is actually exponential, and like the people who aren't very familiar with all these things might think that there might be no polynomial solution at all. So that's not true. We have a polynomial solution, and one of them we found it for O of n to power 5. So O of n to power 5 might sound like it's a lot, but when n is very big, then it can make a big difference. So obviously, O of n to power 5 is a very simple solution using main cost flow. But there is also another thing that is called weighted bipartite matching. Using that, I think we can do even a little better. V square E. Yeah, I think. Wait a second. Yeah, so I can't really find it right now, but maximum weight, matching for bipartite. Hungarian algorithm, yeah. Yeah, okay, yeah, I remember. Using the Hungarian algorithm, you can do it in n square m time. So this can work in n square m time using Hungarian algorithm. So that will be n to power 4 in total. So you have O of n to power 4 solution that will work for n smaller or equal to 100. So yeah, now this is the polynomial time solution. This was just a bonus, as I said before, that you probably won't even care about it, and you should have most probably stopped watching. But yeah, so this is the bonus solution, that is polynomial, and might not work for n smaller or equal to 200, but at least for n smaller or equal to 100. And thank you for watching. So leave a like and comment down below if you want me to do more Leetcode content.